Hey guys, I hope everyone had a good Thanksgiving. I thank all of you for your patience bearing with me. The first week post surgery was a little rough, but here I am. I'm back. Basically, what I want to do is finish just one more chapter this week, chapter 10, and then I will give you guys just a couple of take home problem sets that will be due by the end of the exam period, and that will basically constitute your third exam and the final exam. So trying to be on your side here. They'll both be take home problem sets. It won't be timed. Um, we won't have a final exam during the final exam period. So just let's try to finish out the semester in good fashion. So I hope all of you are well. I hope all your families are well. And I've been isolated and cooped up for about 5 weeks now. So I guess that's kind of good in a way, but I'm kind of nearing the end of my rope as well. So anyway, again, thank you for your patience, and let's try to finish out the semester. So chapter 10 actually is not too bad. It harkens back to one-dimensional kinematics. As a matter of fact, it's just basically a lot of one-dimensional kinematics where particles move on circles. So up until this point, right, we've been dealing with objects moving along, for instance, paths like a block moving along a frictioned or frictionless surface. Okay, and so we realized from the last chapter that we have a magic point here, which is called the center of mass. And for an object which is highly symmetrical, like say, for instance, a rectangular block, then if the block is homogeneous throughout, then the center of mass will correspond to the center of that geometrical shape. Okay, and so we've been dealing with motion, basically of the center of mass of the object, and we call this, this motion translational. So if the object moves from here to here, then we say that this is translational motion. As a matter of fact, if we were to imagine a bicycle tire, and again, if we were in class, I would have this prop with me. So if we imagine a bicycle tire, then we could very well imagine that as long as that bicycle tire is fairly homogeneous, that it's highly symmetrical, that this would be the center. This would be the center of mass. And if we were to exert a force, again, assuming at least at this stage that this is frictionless, and then if we were to exert a force, if we were to exert a force at the center of mass, then this object would translate, right? It would slip along the surface. It would not rotate, right? So this bicycle tire would translate, but not rotate. Okay, because you're going to see that in order to have rotation on this surface, we're going to have friction. So if this is a frictionless surface, then this object will not rotate. But imagine that I'm standing in front of you, okay? And again, harder to draw in 2 dimensions, but I am holding a bicycle tire here. Okay, here's the spokes. And I'm holding here at some center, and the bicycle tire now is free to rotate, just like bicycle tires do, right? So if I were to come in here and slap this, if I were to exert a force, there, then I hope it would be somewhat clear to you that this object would rotate. It would rotate about the center of mass. It would rotate about the center of mass. So the center of mass is here. Right? This is the center of mass. The center of mass is not moving. Okay, so there's no translation. So there's no translation. But there is rotation. And that's the subject of this chapter. We're going to be looking at objects that are going to have rotational motion, right? About some axis of rotation. Okay, so it doesn't need to necessarily be the center of mass. Okay, so this is going to be some axis of rotation. And the axis of rotation is perpendicular to the plane of the board. Okay, we'll talk more about this later. It's going to be perpendicular to the plane of the board. So if we were to rotate both me and the bicycle tire, right? So here I am, rotated. Right, got one eye, it's my nose, there's half my face, and the bicycle tire now looks like this. Okay, so here's the bicycle tire. Then the axis of rotation is here, right? So the bicycle tire is going to rotate about that axis, right? So here's the axis of rotation. Okay. So a couple of pieces of language here. Okay, so we're going to call this bicycle tire and all objects that we're going to consider to be in motion. We're going to call these rigid bodies. And a rigid body is able to rotate, with all parts. This is a weird word. It just means that the object as a whole is able to rotate, right? Such that all of its pieces are locked together. So all parts are locked together without any change in shape. Okay, so we're going to talk about objects that are going to be rotating about some axis of symmetry, and that object is going to have all of its pieces, all of its components locked together without any change in shape. Okay, the center of mass in some cases, or the point about which that object is rotating, okay, is not going to translate. Okay, and so that object will not be in translation. All right, Beautiful. All right. So, so let's begin to talk about the rotational variables, rotational variables needed to discuss this rotational motion. Okay. So let's imagine that we have two objects of mass, two spheres, okay? And these are tethered together on a very light, rigid rod. So this is a light, rigid rod, okay? And these objects of mass are tethered to it, okay? So then one's going to be, one's actually going to be at R1, and one will be at R2, okay? And so now we're going to allow these, objects to rotate. They're going to rotate about the origin. So here's the origin. And so they're going to rotate about the origin. And so there's an axis that's perpendicular to the XY axis that we're going to consider to be the axis of rotation, okay? And so we're going to allow these objects to rotate. And so then mass 1 will be here at some later time. Mass 2 will be here at some later time. So here's mass 2, here's mass 1. And they've rotating about the center of mass. So they're sweeping out parts. Well, that's not very good. They're sweeping out parts of a circle, okay? And I hope that you appreciate the fact that they've both done this in the same amount delta t, okay? So if we start watching these objects at the origin, and then we take a snapshot of them at some time later, then they've both moved, right? They've both moved a time through a time delta t. Now clearly, right, doesn't take a PhD in physics to realize that this object moved to delta S1, and this object moved through a delta S2, where delta S1 and delta S2 are these arc lengths, okay? So delta S1 and delta S2 now are going to be these arc lengths, okay? And I hope it's clear also that delta S2 is greater than delta S1, okay? So now if we were looking back at one-dimensional kinematics, and I asked you to calculate the average speed of mass 1, you would be likely to tell me that the average speed would be the distance traveled over the time of travel, and the average speed for 2 would be its distance traveled over the time of travel. And you'll notice that the times here are the same, but clearly, right, since delta S2 is greater than delta S1, then we know that V average 2 is going to be greater than V average for 1. And there's nothing wrong with that, okay? There's nothing wrong with that analysis. That is basically one-dimensional kinematics. The fact that these objects are are connected to points on this circle. It's really just one-dimensional kinematics. It just looks funny because it's tracing out a circular path, but the kinematics can be aptly described by all of the one-dimensional kinematics that we described earlier, okay? But the interesting thing is that these objects are moving as a unit, right? So they're locked in place. They're rotating about their axis of symmetry here, which is at the origin. And we would like very much to be able to talk about these two objects as an ensemble, as a unit, okay? Because they're rotating about that axis of rotation, right? In a locked-in way, so to speak, to use the language that we developed before, okay? So if you think about this for a few moments, you will recognize that both of these objects, they both sweep through the same angle delta theta, right? So mass m1 moves through delta theta, mass m2 moves through delta theta. So we found a parameter that is the same for both of them, right? In addition to the time being the same, they also moved through the same angle delta theta. So you might recall, right, if you remember some high school sophomore geometry, that if you're looking at a circle, and if you were to look at this arc length, okay, we'll call that delta S, or sometimes we can just call that S, right? So some books will call it delta S, some will call it S. Let's just call it S. And if this is delta theta, which we'll just call theta, okay? And if this is the radius, you might remember that S, the arc length, is equal to R times theta. Okay, and that's a really interesting formula, all right? You'll notice a couple things about it, right? You'll notice that the units on the arc length are meters. The units on the radius are meters, which means now that the units on theta must be unitless. As a matter of fact, theta now must be in units of radians. So theta must be in units of radians, which is really not a unit at all, okay? And so clearly you can see that here, right? This must be unitless to have meters be equal on both sides of that equation, all right? So theta must be in units of radians, okay? Not degrees, right? Not degrees. And some of you might remember that the way to convert theta in degrees to theta in radians is that there are 2 pi radians for every 360 degrees. So that's the conversion factor, okay? So now if we go back, right, this is our little geometry detour here. If we go back to our problem at hand, then we know that V average for 1, which is now going to be delta S1 over delta T, and V average for 2 is equal to delta S2 over delta T. Delta S1 now is going to be the radius R1 times theta, which is delta theta over delta T. And for delta S2, we're going to have R2 over delta theta over delta t. And you'll notice something magical happens is that for both of those objects, mass 1 and mass 2, delta theta over delta t is the same, okay? Because they both sweep through the same angle in the same time, okay? So we call this now, we define a new rotational variable, right? We define omega average to be defined as delta theta over delta t, okay? We call this the average angular velocity or speed. Now we'll talk about the vector notion of these in a second. And speed and velocity I will use interchangeably here, okay? But it's the average angular velocity or speed. And the units now, this is going to be radians. This is going to be units of seconds. So the units now are going to be radians per second on the angular velocity, okay? Which means then up here, this then is going to be R1 times omega average for 1. And then this is going to be R2 times omega average for 2. Okay? All right? But omega average for 1 is equal to omega average for 2, since delta theta over delta time is the same for both masses, okay? So we get then that V average is going to be equal to R times omega average. And you know, as you shrink down, as you shrink down the time window of observation, that is, we let delta t become very small, which is the same as delta theta becoming very small. Then omega average becomes an instantaneous angular velocity. Okay? Beautiful. Beautiful. We also get that this is now then, as we go to instantaneous parameters, that V is equal to R omega. Okay? We already had that S is equal to R theta, right, that we described above. And you can see already we're beginning to build a dictionary here of moving from translational parameters, right, on this side, right, translational parameters on this side, and rotational parameters on the other side, okay? So bear that in mind, keep that in mind. So the last thing to do in this little module, right, is remember that, remember the game we played before, right? We went from displacement, right? Or we went actually from position to change in position was displacement. Change in displacement with respect to time was velocity. Change in velocity with respect to time is acceleration, okay? So there's nothing to keep these objects here from starting at rest and then someone doing something to them that ramped them up to some speed, okay? Now, while I have this diagram here, right, I want you very much to appreciate, okay? I want you to very much appreciate that the velocity, right, which we know is tangential to the object's motion, okay? Whoops. So here's, right, this would be V2. Here's V1. Okay, here's V2. Okay, here's V1. And you'll notice that I drew those vectors with the arrows, basically showing that the farther we go out, the greater the velocity. Now we get some new language here, right? And so you'll notice that these velocities are tangent, right? They're tangent to the object's motion, right? They're tangent to the object's motion. Okay, so the velocity is tangent to the object's motion. And so we give that a name now in rotational kinematics. We call that the tangential speed or the tangential velocity. Okay, all right. And the relationship between the tangential speed and the angular speed, or the tangential velocity and the angular velocity, right, is given by this dictionary. Okay, all right. So lastly, we know that the acceleration is now going to be equal to the change, right, of change in the velocity with respect to time, which now is going to be the change in r times omega with respect to time. And if we're talking about mass 1 or mass 2, right, the radius of those objects are not changing in time. So we can talk about mass 1 being at radius r1, mass 2 being at radius r2. Those radii are constant. And so then this becomes r d omega over dt. And what do you think we're going to call this? We're going to call that the angular acceleration, right? So the angular acceleration alpha is going to be defined as d omega dt. So this is going to be the instantaneous angular oops, not enough friction on this iPad. Instantaneous angular acceleration. Okay. The units now, right? The units are going to be, we know that the units on omega are going to be radians per second. The units on time are going to be the second. And so that's going to be radians per second every second, or radians per second squared. And we're not surprised by that unit at all. Okay. So from the standpoint of units, the angular acceleration is going to have units of angular acceleration. Okay. So then this then becomes then r times alpha. Okay. If we were to talk about average parameters, then the average angular acceleration then is going to be equal to r times the change in the average angular velocity with respect to time. Okay, all right. So now we have a complete dictionary in moving from translational to rotational variables. As a matter of fact, you will remember that we called this the tangential velocity. We're going to call this the tangential acceleration. And sometimes some books will actually write this as a T to make sure that you know that it's the tangential acceleration. Okay, so this is a good place to stop this module, and then we'll pick it up next time and develop the kinematic equations for an object in rotational motion. Okay, thank you very much, and I'll be in touch soon. I will upload the solutions to chapter 10 problems as well. Okay, and again, thank you for your patience.